All right, everyone, we're going to get started. Welcome. I'm Carrie Favaloro. I am a winter naturalist here at ACES, and I'm thrilled to welcome you to our Naturalist Night. We have these every week, and they run because of a partnership between Wilderness Workshop, ACES, and the Roaring Fork Audubon. And we bring in experts from all over the state for these talks. So we've already had 2 great talks this season, and we've got them all winter long. The series runs every Wednesday at 5:30 down in Carbondale at the 3rd Street Center. And here, Thursday nights at 7 o'clock, you guys all found your way here, good work. And we do this every week. And every week it's also filmed, which is why I'm speaking into this microphone, and will be available for viewing on the website. And we're able to do that because we have some wonderful sponsors, and that is why we're able to film. So next week's Naturalist Night presentation is called Adapting to Extremes, Life in Alaska's Arctic. And it's going to be by Andre Willie, who's a teacher at Aspen High School. All right, and so in addition to these sponsors, we specifically want to recognize Aspen Snowmass Sotheby's. They are our featured sponsor for tonight. And tonight we have Adam LeWinter here to talk to us. If you guys have heard of Adam, it's probably because of his work on the film Chasing Ice. And I was actually introduced to Chasing Ice by one of my fellow naturalists, Kelsey Elwood. Some of you might know Kelsey. She's awesome, super energetic, bright red hair. And Kelsey, one night this summer, she was like, okay, Carrie and Tawny, we are gonna watch my favorite movie. And so she gets it all set up, and she sits us down, and we watch Chasing Ice. And at the end of the film, Tawny and I turn to look at Kelsey, and she's sitting there with tears streaming down her face. So this is, I love this story because it really shows how meaningful Adam's work can be. And Adam has done a lot of work looking at Chasing Ice is about glaciers melting. And Adam is an engineer. He works with the Army Corps of Engineers, and he has been involved in the Extreme Ice Survey. And so Adam's work focuses on using incredible time-lapse photography to capture things that are happening in nature that we can't necessarily see with our own eyes. And through his work, we're able to see them better and to learn more. And so tonight, Adam is going to be focusing on the Helheim Glacier, which is in Greenland. And yeah, it's one of the main tidewater glaciers that is draining the Greenland Ice Sheet. How's that sound? Amazing. Did I miss anything? No. Okay, great. So please join me in welcoming Adam.
Thank you. I don't need this. Okay, thank you so much. That was just an incredible introduction. I am really honored to be here, and I thank you all for coming here, especially everyone here at ACES and a part of the Naturalist Nights. I will try my hardest to make this as exciting or more exciting than what's going on down the road at the X Games. Hopefully you'll learn a bit more here tonight. Great introduction and what I've done in the past working with James Baylog, the Extreme Ice Survey. Chasing Ice was about that project, and we were really looking at time-lapse photography of glaciers to visualize and understand how glaciers move, what happens when no one's there to observe it. Now with the Army Corps of Engineers, our group focuses on large changing landscapes and how we can better observe and quantify those changes. So not just the change, but why it's happening. Tonight I'm going to focus specifically on tidewater glaciers. So tidewater glaciers, as opposed to just any other glacier, is a glacier that flows into and calves into the ocean, hence the name tidewater. These are typically the larger glaciers that drain the large ice sheets, Greenland Ice Sheet, Antarctic Ice Sheet, also large ice caps and glaciers around the world. For example, in Greenland, there are only about 5 glaciers that do the majority of the draining of ice, even though there's hundreds of glaciers all around Greenland. And they affect the health of the ice sheets. So if there's more ice coming out through the glacier, then the health, meaning is it growing, is it shrinking, is directly affected. And of course, the end result is sea level rise, and that's one thing that we're all very aware of and worried about. They're sensitive to climate change, and not just air temperatures, but because they do flow into the ocean and they're interacting with ocean water, ocean temperatures as well. These glaciers are extremely large. For example, Petermann Glacier in northwest Greenland is 10 miles wide. They're fast. The Ilulissat Glacier in western Greenland flows up to 45 meters per day. That is, you sit down, set your lunch down on a serac, if you actually could do that, and it would be gone by the time you finished. They're remote. All of the glaciers we work at are either a helicopter flight or sometimes a boat ride away, but they're tens to hundreds of miles away from even the most remote, smallest villages in Alaska and in Greenland. And of course, they're in very harsh environments. There's a reason we don't have glaciers forming in San Diego. You just don't have the type of weather, you don't have the precipitation for these things to grow. And all of that combines to make observing them, studying them, really difficult. Just getting to these sites, we have to take multiple flights and helicopters, and the logistics is insane. I'll show you what we're doing in the future, and one of the hardest parts of it is getting people and equipment all the way up to these places. But we still want to study them, and so we need to come up with unique ways to use technology and novel ideas to understand the dynamics of the glaciers. So if you haven't seen a glacier, just as a good introduction of how large and how fast these things can change, Columbia Glacier is located in Prince William Sound in Alaska. In July 1986, this was a satellite image taken. White is the glacial ice, green is false colored for vegetation and rock. If we look at the same satellite vantage point in July 2014, the glacier is retreated over 10 miles and it's thinned. Now, Columbia Glacier experienced accelerated retreat because the terminus, this is a term you're going to hear often tonight. Terminus is where the glacier ends, where it hits the ocean. The terminus began to thin because it wasn't getting enough accumulation up higher on the ice. And as it thinned, it became buoyant. As it becomes buoyant, it flexes, and that weakens the ice, and so it could accelerate backwards very fast. But retreat is only one part of the story. What you can't see here so obviously is deflation. So just like letting air out of a air mattress, glaciers, as they retreat, as they shrink down, they're also going to shrink in elevation. So if we go to what is called juncture, and it was called juncture because the two main parts of the glacier would converge here. Obviously you can see they no longer converge, but if we fly down to juncture point, this is a photograph taken by James Baylog, part of the Extreme Ice Survey in 2006. And it's easy to see where the ice was in 2006. What's obvious too is this trim line. You can think of this as the bathtub ring or the high water mark of the ice. Everything above that is vegetation, alders, it's green, it's had a chance to grow because it wasn't covered over by ice. Everything below is bare bedrock. And the reason it's bare bedrock is it happened fairly recently. This was in 1983, the ice was up here. So for me, Columbia Glacier, number one, was the first glacier I worked on. Number two, I have a very strong connection to it because I was born in 1983. So just in my lifetime, the ice has changed that much. Not just retreat, but this deflation is really important. If you've never been there, it's really hard to tell what the scale is. That could be 100 feet or it could be 1,000 feet. The reality is that's 1,200 feet. That's the equivalent of the majority of the Empire State Building in one single generation. So these things can change very fast. Think of the amount of water that's in there. And if we look all the way back up Glacier, it's the same story. glaciologists, scientists that study glaciers, have been using photography from the start of photography. In 1964, if we look at Variegated Glacier in southeast Alaska, there was a surge event. Variegated is really interesting because ice builds up high, and then at a certain point, it hits a tipping point, and all of that ice starts to surge quickly down valley. So we look at this aerial photo by Austin Post, pre and post surge. This is fantastic. Now we can see what it looked like before and now and what it looks like post surge. But if you're like me and if you're like every other glaciologist, you want to know what happened in between this. Was it fast? How fast did the ice move? Was it something that was catastrophic, or was it a slow process? And so during the next surge, these happen roughly every 20 years. You can't set your clock to it, but that's what we've observed. During the next surge, the same group of researchers put out an early time-lapse camera. So it was a Super 8mm film camera. I'm sure some people have used those. It's not like the cameras we have now that have a lot of electronics and you can put timers on them. They had a digital triggered timer, so it would physically hit the shutter switch, and took an image every 30 minutes, set up right around here during the 1983 surge. Very quickly, it fills the entire frame. I think it's important to remember none of this had been seen with the human eye before. The time frame doesn't match up with us. We work in minutes and hours, days. We can't see this. We can't sit there and physically observe it like this. So after that setup, time-lapse photography was strongly a new technique to be used in glaciology. If we fast forward to 2006, James Baylog started the Extreme Ice Survey. And now our tools were much more advanced. We used Nikon digital SLR cameras. Their images, very crisp, large. They would print to be about the size of this wall. We built custom housings. Again, harsh environments. It's got to be able to withstand hurricane force winds, snowfall, avalanche, rockfall, birds pecking at the solar panels, all of it. It has to sit out there. These aren't getting visited all the time. We used small solar panels to recharge gel cell batteries and bolted these to rock faces in places that we would hope were secure. Not all of them were secure. The crux of the system was this tiny little piece of electronics. It's an intervalometer or a timer, and the basics of how it works is it looks at ambient light at a certain interval every hour, and if there's enough light to take a good image, it'll turn the camera on, trigger the picture, camera saves the picture, and it goes back to sleep. By using that, we could set out these cameras with one small battery, smaller than your car battery, one small solar panel, and these would run essentially until the battery would fail, right? 5 to 10 years is typical for these types of batteries. And the only reason we'd have to go out there is to physically download, pull off the images off the memory card and download them. At Columbia Glacier, which you saw the satellite images of, we've set up cameras all around this glacier. You're gonna see some images in the next scene. This ice fall back here where you can see that the ice is going down a steep section. That's now completely uncovered. There's no ice there. This whole area is uncovered. And here, a camera at Nare Glacier on the flanks of Ama de Blanc in the Himalayas. This one we put on an overhanging wall because we were really worried about the massive mountain above us and avalanche and rockfall. So the benefits of time-lapse photography. If you just had one image, you'd look at Columbia Glacier here in 2012, and you couldn't say all that much about what had happened in the past. And how is it behaving? Is it advancing? Is it retreating? If we go back to that same site in June 2008, I'm going to highlight where the terminus is, because here's another term you should know, melange. It's all the floating icebergs, the bergy bits that have broken off the glacier and now floating in front of the calving front, or the terminus. Toggle back to 2012. That's the change. 4 years, 2 miles of retreat. And of course, like I said, the deflation, the thinning is there. And with the time-lapse photography, we can see what happened in between. Columbia Glacier can flow up to 45 feet per day. So it's constantly trying to move forward. It's trying to advance, but if the calving rate is faster than the advancing rate, you get net retreat. We had to move the camera because the original location was destroyed by snow creep. I went back to check on that camera and it was gone. I couldn't find it, and it's because we had 20 feet of snow over top of it. Poor placement of that camera. There's that rock fall, now uncovered. Watch as it gets covered back up, put Humpty Dumpty back together again. Even just watching these image sequences, it's hard to remember what it looked like before. Now this is eye-opening for glaciologists, for earth scientists, but for the study, what we're really trying to do, quantify how glaciers react to changing atmosphere, changing temperatures. We need more than just the visual. We need velocities, we need mass flux, how much ice is flowing out of the glacier. And to do that, we need to make hard measurements, distances between each scan, between each image. And for that, we think the best tool is LiDAR, or light detection and ranging. It's a laser scanner. I don't know if anyone has ever seen these or worked with them before, but they work very similar to radar or sonar. Instead of sending out a radio wave or a sonic wave, it sends out a laser pulse. And because we know the speed of light, we can wait for that pulse to be reflected back and measure a distance. So the basic idea is send out a laser pulse and measure the time that we transmitted. That laser pulse will interact with the surface. And I should point out that surface, all of this is tied to a global coordinate system, right? So that point that we're measuring has a latitude, a longitude, and an elevation. It's a real point in space. That light gets reflected back. We log when it was reflected back by looking at the change of time, knowing the speed of light, and knowing the fact that that laser pulse had to travel twice the distance there and back. We can calculate range. And if you do that with a scanner like this one, which can pan full 360, and it can look at 100 degrees vertical field of view, you build a three-dimensional model. These scanners can send out up to 300,000 pulses per second. So our results are millions and millions of points that make up a point cloud. Just like a photograph is made up of hundreds and thousands or millions of pixels, LiDAR data is made up of millions of points. And it creates a three-dimensional point cloud. Here you see Helheim Glacier, which was in the image in the past slide, represented in three-dimensional point cloud. It's colored by height. So here's the melange. Below that is ocean water. And then the glacier going up is rising in elevation. We see topography. We see crevasse patterns. We get a lot of information here, but the best part is this is a full three-dimensional image. Now, we didn't start with results like that. There's been a long development process in our lab and in other labs trying to get to this type of a result. So I want to give you a bit of a history in automated laser scanning at our lab. So back in 2006, my colleague Dave Finnegan developed this system. It's the Hubbard Glacier Terminus Profiler. Hubbard Glacier, it's located in southeast Alaska. You see right here. It's a very unique location in the fact that its catchment area, the accumulation area that accumulates all the snow that then forms glacial ice, is so vast and so high. Mount Logan, which is 50 miles away from the terminus of this glacier, is above 19,000 feet. So we get really cold temperatures, we get a lot of precipitation, and it's right on the ocean. So it's very wet, very moist. For that, Hubbard Glacier is one of the few glaciers that's actually advancing. We want to study it because it's rare, it's an outlier, but also because of this point right here and that fjord right there. As Hubbard Glacier advances, it comes close to pinning, and it has occasionally pinned at Gilbert Point. And this is the ocean. This is a fjord. It has no outlet to the ocean. So when that gets pinned, Russell Fjord becomes Russell Lake. And if you're in one of the rainiest parts of Alaska and in the US in general, North America in general, that lake is going to fill up extremely fast. And so the last time that it pinned in 2002, the lake level rose 60 feet. There's a village down at the far end of this fjord, it's 60 miles long, called Yakutat. There's some of the best salmon fishing in the rivers and in the ocean just outside Yakutat. There's a native village. There's been a long-standing community here, and that is in danger of flooding every time that Russell Fjord gets pinned. So what we really wanted to do was study and track how close the terminus is to Gilbert Point. And to give you a scale, I'll do this a few times throughout the talk because scale is so hard. That terminus, that height, is equivalent to a 30-story building, right? These places are enormous, and it's really hard to understand and try to grasp, even when you're there, even when you're sitting on Gilbert Point looking down at the ice. So how we did it is create a laser profiling system that would send out 20 laser pulses, one every 5 seconds. Again, this was in 2006. The technology was not like I showed before, but it was enough that we could get a line across and track the terminus position. We did it over a very small field of view, 4 degrees, and then we could say when it gets to a certain distance, that's when it's in danger of pinning off at Gilbert Point. All of that data was sent via satellite to a server, and then we would show it on this graph on our website. And you could track, here's 3 different dates where the terminus was. And as it marched forward towards Gilbert Point, we could then start to send a warning, say there's a chance that it's going to pin. This is really useful, but again, it was only this small line, 20 points, and it's really two-dimensional. So after a few years, we deployed a new sensor built by the same company, Regal. They're our research partners, to do a 3-dimensional profile or scan of Columbia Glacier and Helheim Glacier. So back to Columbia Glacier. Again, this all was filled with ice, my first visit in 2007. We set up the scanner just on this mountain right here, Great Nunatak. That was our field of view, 20 degrees. The scanner would scan and create. Now we're starting to see something that resembles a glacier, right? But again, still a point cloud. That's the scanner set up down here in Great Nunatak. Nunatak actually, it means an island in the ice. So when people first saw it, the Inuit first saw this area, that was surrounded by ice. Obviously, it's no longer surrounded by ice. So another telling sign of change. Each scan took 90 minutes. It wasn't very fast. 30,000 measurements in total to represent this small area. We had a 20-degree field of view, and we could only run it for just under a day, 22 hours. It had to be powered by a generator. It had to be manually started every single time we wanted to scan it. So it was a lot of work, a lot of human input, but still we got great results, and this was a step forward. What we're able to do is look at subsequent scans and compare similar surfaces, look at where did a point move between one scan and the next. And we can get displacement, distance, and divided by time, we can get actual velocity. So here you see the point cloud colored by velocities, and this agrees really well with what we observe and what we expect to observe at a glacier like Columbia. On the margins where there's more friction, it's moving slower. That's the blue lower speed points. And then towards the center, the main flow line, it's moving faster. So again, really good success, but the scan time was really long. We were only looking at this small slice of the glacier, and it doesn't give us all the information we want. So we took a step back from looking at long range and decided to really hone our skills in automating the system, getting something that can stay out there, be powered, and run without human input. And we did this at Mammoth Mountain in California. There's a long-running snow study site at the, if anyone's been to Mammoth, it's at the mid-base, or the midway section for the gondola. It's blocked off, and there's a huge amount of sensors that are looking at snowpack, snow accumulation. So we built this custom housing, put in the next generation laser scanner. This one could take 10,000 points per second. So we're getting faster, we're getting higher resolution, higher density point clouds. And we had power from the resort. We had a network connection, DSL, so we could log into it and check in it all the time. So we were really well set up. We started it in February 2011, and we scanned every 15 minutes of the snow surface, just about 150 meters distance from the scanner. That 150 meters is because the laser pulse on this particular unit does not interact very well with ice. Ice essentially looks black, snow looks black to it, and so after a certain distance, it's not getting a strong enough return. But it was strong enough to look at the entire snow study site, and from that we could get things like accumulation rates, snow deposition, how wind transports the snow across the site, and melting rate throughout the winter. Now we have a true three-dimensional time lapse. This is the start. If we look at this full first season, 2011, watch the trees back here. Snow surface is various colors, ground, dirt is red. Watch these trees pop up. We had 10 meters of snow this year. As it melts out, again, it's visual, but it's so much more than that. These are all numbers, they're all velocities, all magnitudes. So we can actually get volume out of it. So in this next video, I took a small section, and we have a ground surface and the ice surface, and we can calculate the volume in between that and compare it to melting rates. So green is the ground, white is the snow surface. And this is through June and July, how it's melting out. Look at the sun cups forming. In each one of these scans, we calculate the volume of snow in this one area. So now we'll compare that to the actual measured melt rate in milliliters. And of course, it's inverse. Now, this worked great. We got it automated, but we had power, we had communications, and we had a very short range, only 150 meters. It's not going to do anything on a glacier like Helheim Glacier, which is 6 kilometers wide. So after another couple years of development and working with Regal, they gave us, well, they didn't give us, we bought this scanner, the VZ6000, for a lot of money, and started testing it at Hubbard Glacier and Helheim Glacier in Greenland. So Helheim Glacier, satellite image, it's 6 kilometers wide. It's on southeast side of Greenland. And as I said at the beginning of the talk, this is one of the main glaciers around Greenland that drains the ice. There's hundreds of glaciers all around Greenland, but none of them have the volume that just a very few have. Give you an idea of scale. Here's where we set up the scanner in 2013, looking out across the valley. And here's my colleague down on the margin, looking out all the way across to this area. One thing to note is the crevasses on the margin where it's higher friction, slower flow rates, they're very different compared to that center area. Much larger because they're moving faster. It's more broken up. The scanner is really what changed the game. We have 6 to 10 kilometers range on snow and ice. We get that because it's a 1 micron laser. So it's not eye safe. I couldn't bring it here and run it. Everyone in here would be blind. But it gives us enough power and it interacts with snow and ice really well, so we get that long range. And it's extremely fast, up to 300,000 pulses per second. And each one of those pulses can have multiple returns. So if you think of a flashlight beam, it starts maybe 1 inch diameter, and then it diverges, and it interacts. If I was to shine a flashlight at you, I would hit most of you, right? Same thing happens with the laser pulse, and everything that that laser pulse interacts with sends back a bit of energy to the sensor. And so we can get hundreds, essentially an unlimited number of returns from each single pulse. It's portable, it fits in a backpack, though it's quite heavy. We were carrying it around Aspen Highlands today, and I can attest that it's heavy. Our first test run was at Helheim Glacier. We ran the scanner every 6 minutes for half a day. We had really hard weather, a lot of snow. The next one was at Helheim Glacier, and we ran it for every 30 minutes for 5 days in a row. This was great. The scanner performed perfectly. And again, just like we did with the earlier scans at Columbia Glacier and with the Mammoth, we could compare subsequent scans and get velocities. So here's Hubbard. We had to dig out about 3 meters of snow to even get to a steady platform to put our scanner on. We had a scanning radar set up as well to do comparisons with. At Helheim Glacier, we had much better weather, much better conditions. The scanner was working perfectly. Everything was running really well. Give you an idea of the range. Okay, over 7 kilometers range just from this single site. I want to point out too, all of this data, it's collected from the ground. This is a terrestrial-based scanner. It's from one single position. But if you can see it with the naked eye, the scanner can pretty much see it to a certain range. So while it's three-dimensional, we're doing it from one single point. And on this trip, we started to work with automation and trying to let the scanner run on its own with power and programming. And if I got really scared, I could log in with my iPad to the scanner, check to make sure that it was running, working fine, and go back to sleep. This doesn't bode well for the field scientists because, well, it's all working well, and we just set it up, and my colleagues here were, you can't tell, but that's a GIS fundamentals book that they're studying for teaching a class next semester. But for what we're looking to do, this is great because we don't have to babysit the scanner. On this test, we had a generator running and we had a battery as a backup. And with both of those combined, the scanner could run for 13 hours without any human input. But we want to go further. We want it to be working on its own. An example of what these data look like, again, scanner was right here. It's all collected from that one point, but because it's three-dimensional, we can fly through it. This is Hubbard Glacier in Alaska. You can see crevasse patterns. We color it by height, and you can see topography. Glaciers mirror the bedrock in which they flow over. Go down to look at the terminus. Again, 100 meters tall or a 30-story building. It's colored now by reflectance. Darker ice reflects less light back, and so it looks darker in the scan data. The detail in this is amazing. Just remember, in 2006, we were getting 20 points, 1 point every 5 seconds. Now we're getting 300,000 points per second, and we're measuring 7 kilometers up glacier. Going to Helheim Glacier, we had an even better vantage point. We had better weather, better atmospheric conditions, and so this is what the point cloud looks like. Terminus right here, this arc, all the blue is the melange, the floating icebergs. You don't see any open water in front of Helheim Glacier. Rarely do you see it. There's 100 feet thick of floating ice before you hit sea level. We fly past bedrock. Now at the margins, we have smaller crevasses getting larger as the flow increases, the speed increases. And all of these surfaces, they're identifiable as crevasses, seracs. So we can look at those and we compare them between subsequent scans. Now we can make true measurements. Again, we're flying through 6 kilometers of ice here. you would be maybe that tall. So if we look at just 2 scans 6 hours apart, colored, first one is red, second one is white, it almost looks like it's in stereo. Because the glacier here, Helheim Glacier, moves up to 1 meter per hour. So over 6 hours, you'd expect we would have 6 meters of movement. So you see these surfaces mimicking, mirrored as it moves forward. Now if we play 5 days of LiDAR time-lapse, this is a top view. Moving back and forth, you can see flowing faster in the center. Let's zoom in a little bit more. If you watch it closely, you can see bobbing in this back area. It's going into the ocean, and the ocean has tidal change. That bobbing, again, remember what happened at Columbia Glacier. When it became buoyant and thin enough, it weakened. So if you look at a cross-section, Melange Glacier terminus, it's bobbing. The next one, you can see the bobbing even more. I'm glad you guys think this is cool, because I'm... Now, to get the actual displacements, the distances between surfaces from one scan to the next, we actually took a technique from medical imaging, sonogram imaging. It's called coherent point drift analysis. And what it does is it takes 2 point clouds. It's hard to see in here, but you can see it better in this animation. 2 similar point clouds, and it looks for surfaces and clusters of points that are the same. And then it fits it together. And that movement that it needs to create is then translated into a magnitude vector, or a distance. Now we have a distance, we know the time frame, and so we can get actual velocities. So we look at the results, what we're really interested in. This graph is made up of tiny little arrows whose magnitude is the actual displacement between 2 scans 12 hours apart from this small section on the glacier. Not small, that's 400 meters by 400 meters. And by looking at the magnitude and the time, we can say we're getting from 0.83 to 1 meter per hour velocities. This is key. This is what we've been looking for the whole time. Now we can calculate, knowing the depth of ice here to the bedrock and the velocities across the glacier, we can calculate how much ice is passing through this gate. And that goes really far for us. And not only how much ice is passing through the gate every month, but every 6 hours. So those diurnal changes, the daily changes, the tidal changes, those are really important. That's why we want to be able to do this faster than something like a satellite can acquire. So combining all of these things, we're now moving into the next phase of our project, which is the creation of an atlas system. The past systems, low resolution, meaning low point count, short range, 150 meters isn't going to cut it, or the study periods were too short. 5 days at Helheim Glacier was great, but we want to know what happens throughout the whole winter. We want to know what happens throughout multiple years. So we've combined all of this research technology into the autonomous terrestrial laser scanner, or a little less nerdy, the Atlas system. And we're basically bringing everything that we've learned from past studies together into this future project. It'll be fully autonomous, meaning all of the power, control, communications will be on site. We will set it, we'll program it, and it will run on its own. We can program the scan interval so we can get that 6-hour time frame. Multiple scans per day will give us the diurnal and tidal fluctuations. And we'll be able to communicate with it via satellite. So we'll get health updates, we'll get reports about how it's scanning, and if we need to troubleshoot, we don't need to fly up to Greenland, spend $25,000 in flights and helicopter chartering just to go there and see that something is not right in the program. We'll be able to communicate with it from anywhere. That's the system. And of course, it's not eye safe. We're using that long-range scanner, so we will have to put one of these signs, or maybe something a little more professional, up at the site. So let's run through just the basic schematic, all the components that go into this system. And again, I should say, we're going to install this at Helheim Glacier. So first, the heart of the system is the laser scanner. It's the same VZ6000, the long-range scanner, non-eye-safe scanner, inside a custom housing that is being built, designed and built for us. It has heating and it has cooling. It has a smart controller that keeps it safe. If there's high winds, it'll turn and park into a window shield to keep it from getting sandblasted. 6 to 10 kilometers range, 222,000 measurements per second. It's a little lower than the 300,000 because we want to have longer range. It is fully autonomous, so we set it and forget it. We have weather station sensors that will be set up to help calibrate and adjust the measurements. So when you're shooting through 6,000 meters of atmosphere, there's going to be rain, there's going to be humidity, the pressure will change, the temperature will change, and light is affected by all of these things. So we'll do real-time measurements to calibrate and adjust the point cloud. Each scan will be made up of 30 million points, and of course it's ruggedized to withstand the harsh Arctic environment. We have a battery and control system, so lithium iron phosphate batteries that are being recharged via solar, wind, and methanol fuel cells. In Greenland, in our location in Greenland, we have a long section of the winter where we get no direct sunlight. So solar's out of the game. If there's no wind, which happens often, then wind's out of the game. The battery pack will drop down, so we incorporate methanol. We use smart charge controllers to keep these batteries happy and healthy. A data logger, that small piece right there, that's the brains. That's what's controlling everything on the system. It'll take all the weather station data and send it to the scanner. It'll tell the scanner when it's safe to scan. We have 3 satellite communication modems, one to use as regular and 2 backups because, again, $25,000 to get to this site. We don't want to take any chances. And the two-way communication is key. We can get health reports and we can make changes. We have our towers of power that also house the climate station data, sensors, and we're using 6 large solar panels. These are the same size as you see in most residential installations. 2 400-watt wind turbines that are hardened for high winds. Winds have been recorded at outlet glaciers in Greenland up to 200 miles per hour. We're hopeful that that doesn't happen because I don't think that these are going to withstand it, but they can withstand up to 100, 120 miles per hour, which is more common. And then all of our satellite communication antennas will be housed on the power tower. And then finally, this fuel cell fueled by methanol. This is key because, as I said, in the winter we might not have solar, we might not have wind, but we will have something on site that can keep the batteries running. And the setup that we're putting in could keep the scanner running for 106 days without any other input. So going through all of this struggle to run out of power would be a real bummer. It turns on when the batteries need it. So if by chance the solar and the wind are good enough and they keep the batteries charged, then this thing will never turn on, but it's there for backup. The way it works, at a certain interval, every 6 hours, the data logger will turn on. It'll grab all the climate station data and the battery health, and it'll assess if it's okay to scan. Are the batteries charged up enough? Is the wind low enough? And so on. If it's not okay to scan, it'll tell the scanner, we're not scanning, you're not getting turned on. It'll go back to sleep, go through the interval again, and start again. If it is okay to scan, the scanner turns on. If it needs to be heated or cooled, that'll happen. I doubt it'll ever need to be cooled up in Greenland, but it's an option. When that's done, we send back a health report. We send back how many points were measured, a small 2D image of the point cloud. These point clouds are very large. We couldn't send it over satellite communications. And that gives us a verification that the system's working, and then it just turns off, goes into a sleep mode until that next interval starts. This is what it's going to look like. It's not actually installed there, but my friend did a very nice job at rendering it. It's a CAD model. That's how we're going to set it up at Helheim Glacier. So everything's going to be on site. This is the first of its kind. No one's done this type of installation before, mainly because the technology just did not exist. We are going to install it in June 2015. So we're filling a 20-foot cargo container that's going to ship up to Greenland in May. It's going to scan every 6 hours. We'll get that daily and tidal fluctuation that we really want to get, that satellites cannot get. And we'll be able to calculate that thing that we're looking for, glacier mass flux. All of this is going to be used to better understand how Greenland's ice, how Greenland's glaciers react to a changing climate. And the nice thing about this is this system doesn't have to be used just on glaciers. If we bring it to Aspen, here's the Highland Bowl. We've been doing a study for the past year and a half looking at avalanche terrain, making snow depth maps, snow depth change maps, looking at slab thicknesses on avalanche terrain inbounds at resorts. We've done the Highland Bowl at Aspen Highlands and many faces at Arapahoe Basin. By scanning the Highland Bowl, now it's colored by intensity. That's how much light is reflected off of different surfaces. So snow reflects different than trees. Quickly, we can make a slope map, and that goes from 25 degrees up to 90 degrees. Trees obviously are vertical, but look, this is dangerous avalanche terrain. There's a reason why there's such a strong control program at Aspen Highlands. And then if we compare subsequent scans, we can get snow depth. Here you can see the hiking path, areas where the boot pack program has done a really nice job. If we go to the east wall at Arapahoe Basin, we did this study all last year. My colleague Jeff Deems is here, who was running this study, where we scanned pre and post snow events and pre and post control. We look at this image, this animation. The first image is just snow depth, total snow depth for this winter, 0 to 4 meters. So high accumulation. Next, it's going to change to snow depth between 2 dates or one snow event. Red means that there is, in general, an accumulation. And what's really cool is you can see some duning from slab events. Now, just from 2 control explosives, the entire face ripped out. Again, it's 3-dimensional point cloud. We can measure slab thickness. We can measure the crown height. We can measure the volume of snow that is accumulated down at the bottom. By seeing that it's white, that's about 0 change between the 2 scan dates. That means that the last deposit, the last snowfall, ripped out completely, and in areas where it's blue, it actually went down below that layer. So this tool is useful for so many different types of things. So in the midst of this project and all of the obsessing over the science and the technology, I first started working up in these places as a photographer. So I can never forget about how incredibly beautiful they are. Glaciers like Helheim Glacier deserve our attention. They need our attention. The next animation or next video is something that I shot with Jeff Orlowski as part of the Extreme Ice Survey during nights with the aurora. And I watch it to remind me why I'm doing this, why we need to study these places, why we need to learn. So I hope you enjoy.
have time for a few questions. And before we start the question and answer section, I just want to remind you that we are filming this and all the audio is collected through a microphone. So please wait until the microphone reaches you to ask your question, or I'll have to repeat it into the microphone. Yeah.
Adam, you did a great job explaining the technology that you're using. Can you talk about some of the applications of all of this information that's coming in?
Mm-hmm. Yeah, so some of the applications for this information, obviously one of the big things that we study glaciers for is the health of the glacier and how it contributes to sea level rise. So we're working with oceanographers that are making measurements in the fjord just down glacier. And by combining that with how the ice moves and that ice mass flux, we can get better estimates of what we should expect for sea level rise contributions from Greenland.
Other questions?
Really early photographs show us where the glaciers were, and I'm just wondering, especially in Southeast Alaska, where there's so many First Nations people that are still there that have such intact oral histories, in a place like Hubbard Glacier, where you have the town of Yakutat, where people still live and have lived for hundreds of generations. Have you ever considered sort of supplementing photographs with their stories of their town flooding, maybe?
Yeah, so the question is using local people that have lived there and experienced these changes much more than we have for a history. And yeah, of course, the glacier, Ilulissat Glacier, it means White Mountain. It means White Mountain because right where that village named Ilulissat is where the glacier used to be. And they named it White Mountain because that's what it looked like. The icebergs looked like giant white mountains coming out. And when we go to places like Ilulissat or Yakutat or Tasiilaq, you can't help but I introduce myself and I say I'm studying the glacier, and I immediately get stories about what this place used to be like. Not only where the glaciers were, but the bigger one is sea ice, where the sea ice extent, especially in Greenland, where Greenlanders love winter because their range, their area that they can move around in and hunt and fish and have activities increases exponentially because the sea ice freezes and now there's this great big flat area. They express to us sometimes quite emotionally because they look at us and say, it's your fault. It's not our fault. But how they've seen in their lifetime and in generations before them and with their parents and grandparents. And I know of a few people that have done research by just taking accounts, human accounts of what these places used to look like. A tentative question back there.
I'm just wondering what you envision to be the next step. Like, what do you see happening in the next 10, 15 years? That's a really broad question, but if you have any feedback.
Do you mean as far as the technology for observing?
As far as the laser technology,
Sure.
and it's come so far since just 2006. I can't imagine it won't keep progressing.
There's a development between both laser technology, which we're working on, and photogrammetry. So just taking images from multiple locations and creating maps. And those work hand in hand, and in some places the photography works better, and in some places the LiDAR works better. I think the LiDAR works better all the time, but the sensors are going to be smaller, they're going to be less expensive, and they're going to be easier to run autonomously. That scanner right there is $250,000 US. I go to the factory and I work. They're based in Austria. Work with their engineers to develop sensors that we want to use, and so I understand that the amount that goes into this, it is worth that money, but it's extremely expensive, so most people can't get that kind of funding. We have a foundation, the Heising-Simons Foundation, that is funding the hardware, a big chunk of this project. So we're really fortunate that we can do it, but for all the different glaciers that we want to study, it's not reasonable, right? The whole system is $500,000. how many glaciers are there? It's really not going to work. So obviously smaller sensors, better ways of communicating with it via either satellite or cell repeaters. And I would love to envision having a little hangar out there that sends out a drone that flies across the glacier and flies back and images the glacier much higher resolution. Really technology has gone, if you look at what we've done from just 2006 to now, I don't think that's unreasonable, and obviously it would take a lot of work, but we will see big changes. Yeah, up here.
Is your organization or someone else doing this in Antarctica?
Yeah, so the question is, are we doing this in Antarctica? Right now we have just enough to do it at one glacier in Greenland. But I am going to Antarctica next October for a project which will obviously not be a long-term project, but we will be doing similar type work. And there are many other researchers that are doing laser scanning, repeat photography to create three-dimensional maps. So yes, there's in our lab and in all the other research institutes and universities, there's work going on.
All right, we have time for one more question.
So this is all very fascinating. I appreciate it. What's really cool is being a part of this many people on the planet Earth is that you can do what you do and I can do what I can do. And with all your experience, what wisdom or advice would you, I guess, leave with us since you'll continue to go down this line of path in life while we kind of do our thing, what could you leave with us with all the experience you've had in it?
I would say find your passion, find what you're good at, and find what you're an expert in. This project, we have many people, scientists, engineers, writers, filmmakers. In past projects, I've worked with every type. And what I could do better than my colleague, they could do something better than me. And they had a better idea of how to do it. And so all of us are experts in something. We're passionate about something. If you're a teacher, you can teach well. You can be passionate about it. If you're an engineer, obviously something like this is possible. But I think all of us would benefit by doing, what we love and what we're really, what we feel strongly about. And whatever that is, as long as it's something. I don't know, it's kind of a broad thing.
Thank you.
Yeah.
Adam, thank you so much for joining us tonight, and thank you everyone for showing up. We hope to see you at future Natty Nights.
Thank you.